All right, we are back for another episode of the TFD Performance Podcast. Now, if you were a fan of the Fight Science Podcast, today's guest will be no stranger whatsoever. We are welcoming back Dr. Oliver Barley, all the way from Perth, Australia. Dr. Ollie B, thanks for coming back on.
Thanks for having me on, Geordie. I'm happy to be back. Have I got the record now for the most amount of appearances, or am I tied?
You're definitely up there. I was thinking about this before. This is number 3. Is this number 3 or 4?
Yeah, it's been number 3, I think.
Number 3. Yeah. I think you're definitely up there. Well, to be fair, there's a lot of people, when I get them on, they talk about their topics of expertise, and there's really not a lot to cover. And then everyone that I keep getting on, like yourself included, it's like we can talk about one topic, but all of a sudden you're an expert in all of these other topics. So It's just rude not to get you back on, right?
Well, look, I'm happy to be here.
So we're going to talk about a couple of things today, Oliver. Me and Oliver just spoke pretty in depth on offline there, and I really want to bring these topics back up. But we're going to cover two things that are really, really important, not just for the combat sports world, I think for all athletes, but we're going to wind this one back specifically for combat sports, MMA. Dr. Ollie B, not only is he world-renowned expert in many, many different areas, he's also an MMA coach. I don't know if you guys know this. What are you, BJJ purple belt? Doctor?
Yeah, BJJ purple belt. Most of my experience and what I'm doing most of my coaching in is for striking. I've been striking consistently for 20 years or something.
BJJ really purple belt, kickboxer, MMA coach, science was extraordinaire. So we're going to combine all of them today, and we're going to talk about a couple of topics. The very first one that I want to talk about is one we have spoken about before, but I want to clear some simple myths and I want to get some facts out there. It's hydration. I think hydration in terms of sports nutrition can be one of the most simple things if you want it to be. And then when you really start deep diving into it and thinking about it a lot, it's probably one of the most complex areas in all of sports.
Yeah, look, hydration's a difficult one because it seems so simple on the surface. So when you think about nutrition, at least you can talk about with nutrition, hey, look, there's carbohydrates, there's fats, there's proteins, there's fiber, there's vitamins, there's all this stuff. With hydration, it's more or less people just thinking, what's water? It's like one thing that we're kind of trying to manage here, which I guess is true, but it's an extremely difficult thing to manage. And it's very acutely impactful as well. So it's a big topic. And obviously I've dedicated a great deal of time to trying to understand it better, which is why it's so funny to me when people claim like they've got very simple solutions to problems that I'm like, why didn't I think of that? Which really it's not even that at all, but
it's funny. We were just talking a little bit off air there about how I received some messages about someone who has seemed to solve all of these problems that Oliver and many colleagues around the world who have dedicated their entire careers to solving this hydration puzzle just seem to solve that they haven't. So it's a very interesting one, and a lot of people seem to think they understand it, but really the reality of it is it's a very complex thing. So I want to dive into it. Let's just start very basic.
Yep.
What is hydration? What's your definition of hydration?
So basically what we're looking at is your body is 50, 60-ish, maybe a little bit more percentage water. So more or less you're just kind of a giant walking water balloon. Essentially, like, water is used as the basis for a lot of chemical reactions across the body. So more or less everything that's happening inside of the body, for a large part, requires water in some degree of instance. Now, hydration, because it's actually an interesting topic, and I'm trying to remember where, because basically what we have is a couple of terms, so hydration is referring to body water overall. And we can think about that in terms of statuses. So for example, the term dehydration actually doesn't mean what a lot of people say that it means. So dehydration is the process of reducing body water. Someone having low body water is actually called hypohydrated. Too much body water is hyperhydrated, and then the right amount is euhydrated. However, again, in the area of dehydration research, it gets so messy because I even publish studies where I use the term dehydration when I actually mean hyperhydration. And the reason I do that is because that's what it means to everyone else. But like languages, the purpose of language is to convey information. It doesn't really work if I'm using a word that no one really understands. Even it's kind of like how the dictionary had to change the word literally to have a definition, which was figuratively because people were misusing it so much. Yeah, so it's mainly about how much water is in your body. But the thing is, we focus a lot on how much water is in the body. But I think that's actually probably a very overly simplistic way to look at it, because what also matters is where that water is inside the body. And that makes a huge difference. So for example, if you do, if you start exercising at the exact same intensity, one of the things you'll notice is your heart rate starts climbing upwards over time. So if you're running, I don't know, 14 kilometers per hour or something, and your heart rate is 145 or whatever. If you do that for an hour, at the start, it might be 145, but at the end, it might be 165 or greater. And there's a couple of things that can cause that. But if I think of one that isn't affecting total water, is when your heart rate goes up, your blood pressure goes up, and what happens is you get an increase in osmotic pressure, which is basically just force on the inside of the blood vessels. And that actually forces a bunch of the water out of the blood vessels and to just float around in the cells. And that very acutely drops the amount of blood volume, even though the total amount of water in your body hasn't changed. So actually, body water, we're not just talking about a total, it is about that location. And body water not being in the right place, because that's the point I've made ages ago, is that if I suddenly dehydrate myself 2 kilos and I do that really fast, and then I scull 2 liters of water, am I rehydrated? Like, the total amount of water in my body actually is probably back to what it was before. However, 2 liters of it is sitting in my stomach. So it's not, it's a difficult topic for kind of that reason, is I think people look a lot at retention and or look a lot at basically how much water is in them on total. But yeah, it's complicated.
So right out the get-go, I hope you appreciate where we're going with this conversation. Even the definitions of what we say, euhydrated, hydrated, dehydration. I'm pretty sure I've even said euhydrated to someone and gotten into an argument whether that should be used in the academic literature or not. But let's go right back and let's just talk about this, and let's say how much water is in the body and what are these different fluid compartments when we're talking about where it is.
So basically what we're looking at is the water is kind of located in a few places. So obviously how much water total depends on someone's body size. It's basically based on a percentage, but the fluid is located in the blood, in the so inside the cells, and then in that fluid in between the cells. Primarily is what we're kind of talking about, is you've got blood fluid that goes from the blood to the fluid in between the cells, and then fluid inside the cells themselves. The majority of that fluid, the fluid of your body, is inside those cells at any given point in time, with a smaller percentage of it being in the blood, which makes sense because obviously you have a lot more weight of cells than you do weight of blood. Yeah, so basically that's what, and it's understanding those different compartments, which I'm just trying to pull up, because I've basically got a ton of my paper, various papers sitting in front of me. I'm just trying to pull up various ones to make sure that I don't mothball any of it, because I constantly forget what I've written because my brain is so smooth. No, it's because there's too much to remember. That's the whole point. But basically, yeah, so approximately 30 to 35% is that intracellular fluid, and 20 to 25% is interstitial, and then 5% of that is then inside the plasma. So essentially what we're looking at there is trying to understand, because, and then by the way, that's not accounting for fluid that would just be sitting in the stomach or in obviously the digestive system. And essentially one thing to remember as well is that the fluid moves in it's kind of like going up gears in a car. You're not going to shift from first to third. You're going to go 1 to 2 to 3 to 4 to 5. And it's the same deal with how fluid moves around the body. So I remember ages ago, I was in the gym and I was listening, and I went during bro hour because I wasn't able to go before work. I was just listening to someone like, bro, you should take this supplement. It bypasses the bloodstream and gets straight to the cells. And I was like, what? I literally don't know what it's teleporting. So essentially what we do is if we pull blood out of the cells, not blood, water. If we pull water out of the cells, that's then poured into the interstitial space, and then that's then poured into the blood, and then that's ultimately poured into the urine or to the sweat glands, and then that's expelled. If we re-put it in, obviously we're re-putting it into the stomach. That flows into the blood, and then ultimately has to get into the interstitial fluid, and then ultimately into that intracellular fluid, or the fluid inside the cells. And one of the things that makes hydration kind of complicated is your body doesn't really have mechanisms to move water around actively. A lot of it is based on osmosis and osmotic pressure, which essentially is based on the concentration of that fluid. So that's one of the things that makes it interesting. And one of the points I've mentioned about dehydration before is that when you lose sweat, you're losing both water and salt, and also chloride and a couple others, but salt's the big boy there. And if you're re-putting in pure water, obviously you're replacing that water, but you're not replacing the electrolytes. And ultimately that affects how the blood moves from one compartment to the other and what speed that it does that. Which basically puts us in a position where we've got a lot of water across the body, but it's more or less like, spinning plates. There's a bunch of these plates spinning, and it's trying to get them all balanced correctly. And dehydration certainly makes that more difficult, which I think I'll let you jump in because I just keep talking otherwise.
I was going to say, let's define a couple terms here before we get going, just to help guys follow it, because we're going to get deep. We're going to get deep here, and you need to get deep so you can appreciate the complexity of this topic. Osmosis and osmotic pressure. Can you define them and then talk about how they change, why we're going through this state of dehydration, which for the listeners, remember, is that more dynamic process of losing total body water to arrive at a state of hypohydration where we've got less total body water.
Yeah, so basically osmosis is, I teach it in a couple of units, and I always find it can be quite difficult to teach. So if we think of diffusion, for example, so basically diffusion is things will spread out from high concentration to low concentration. If you fart, there is a high concentration of fart near you, and that spreads around the room until it kind of moves out. So it's diffusion. Now, osmosis is similar, but for water. So essentially, water will move from high concentrations of water to low concentrations of water. Now, essentially, the way this gets taught can confuse students a little bit, because we talk about going from a less concentrated solution to a more concentrated one. So they think of it going from low pressure to high pressure, or low water. But what they're looking at, but I think the easiest way to explain it is it's from higher concentrations of water to lower concentrations of water. So if you have a solution here that has, I'm going to randomly 99 parts water for 1 part salt or something, and then we have a membrane that the salt can't pass through, and then on the other side you've got 95 parts water for 5 parts salt. The water will actually move across until the water parts are evenly distributed across them. And that, when you think about it, is exactly what the body is doing, like 4 times or whatever. So it's moving from the stomach, or from let's call it digestive tract, because stomach wouldn't be accurate. You actually don't get water across in the stomach, it's the intestine. The digestive tract into the blood, that's doing that once, and then from the blood to the interstitial fluid, that's your 2nd time, and from the interstitial fluid into the cells, that's the 3rd time. So essentially it's passing through these membranes, but based on that pressure and that concentration I'm talking about, so the parts water versus parts salt, that's basically how osmotic pressure gets defined. And basically, obviously the osmotic pressure in that case, in the example I gave before, is causing fluid to move across into the more concentrated solution. And essentially that's why, imagine in this case, we've constantly got things moving from one to the other, and that's going fine. But then if I pull a bunch of salt out of them, suddenly that flow changes. And even if I put the water back in, it isn't necessarily going to move in the same way. And that's where this all becomes an absolute mess, is essentially how poorly we understand the movement of fluid across those compartments, and how poorly we understand, especially in a sports setting, the way that we should be managing that. And there's actually dehydration might be one of the oldest arguments in exercise science that is still currently being had. Like, you know, there are some arguments that have been had at some point and have ultimately been resolved, but dehydration has been argued about long before I was born, and it's still going now. Like, it's kind of ramped down a little bit because we've reached general points of agreement, I would say, as a research body. But I would not say a lot of it, people have just kind of gone, I'm so tired of fighting about this. Let's argue about the keto now, even though they haven't actually solved the dehydration problem. But I think there's a lot of agrees to disagrees, I guess, or we just don't know being accepted.
Yeah, I feel like it's one of those things that if it's not a pertinent part of, say, what you have to do in your day-to-day, whether that's your work or your job or your training, a lot of people just brush it to the side. Obviously, you and I are in combat sports where weight cutting is hugely prevalent. So we have to understand this stuff. But say if we're just looking, you know, at a housewife who's staying at home every single day, yes, they're going to have to drink water to meet their daily fluid needs, but it's like knowing the intricate details probably aren't that much. But something I just want to touch on, Oliver, before we keep going, because I want the listeners to understand this. So what we're saying is that osmosis is this movement of fluid, and the movement of fluid will happen because of different concentrations of these solutes from different parts of the body. And we've got all these solutes spread out and they're separated by different things in the body. So we've got this one component, which is inside our cells, our intracellular space, and there's going to be a certain amount of solutes in there. Then outside of it, we're going to have the extracellular space. That's going to have a certain concentration of solutes in there, like our electrolytes and sodium and everything else. And then you're saying outside of that, there's going to be the blood, and then there's the skin. And through all those different components, there's different solute concentrations, and that's what's creating this osmotic pressure that's dictating where the fluid goes between these compartments. Is that right?
Yeah, definitely. Exactly. There you go. You summarized it better than I could say it.
Well, and the reason this is why I want to ask you this next one is because, well, what happens when we start losing this fluid? Like, how does our body figure out, okay, well, let's just move this to here and this to here. We're moving it from here. There's so much going on. Like you said, there's just all these plates spinning. How does our body figure it out?
So it's kind of funny, but I guess it kind of doesn't, in that it more so just goes, so when you're losing fluid, it's usually like the body doesn't really want to lose fluid. It just needs to use it as part of just being alive. So used in metabolic processes, every time you exhale, you're losing vapor through that way. Obviously, sweat being the one that we talk about most. And sweat is probably the one that has the greatest upsetting effect on this balance, because when you lose fluid through vapor out of the mouth, you're not losing those solutes. And generally speaking, throughout the day, the amount that's being cleared out in the urine, you're not losing significant amounts of these solutes that are likely to actually affect your day-to-day function. What we do see is in the case of sweat, because you have to, first of all, to get water into the sweat glands, there has to be salt inside the sweat glands, because that pulls fluid into them. So by very virtue, the body has to be outputting salt just to get that water out. So it's essentially sacrificing salt to get the water to move into those glands so that it can then be ejected throughout the body. So essentially what it's doing is it's going, well, look, the body kind of works based on priority. And what it's doing is it's going, we're going to die of we're going to die of overheating. All right, just cool it down. It's like, oh, but we're going to lose water. It's like, we'll deal with the water loss later. Heat first. And essentially what's happening is it's just booting out all this water to then ultimately cool you down. But then afterwards it's going, oh, oh shit, what's happened here? And what's then ultimately ends up is we end up losing a lot in the blood, which then affects the concept. You lose more water than you lose salt, but you do lose a lot of salt. So then the blood becomes more concentrated, fluid gets pulled across, and the fluid ultimately ends up shifting all the way across. And I've actually just spaced on exactly where I was going with this. So this is a problem with hydration. I just keep talking.
So it went to the blood, and then so we're pushing fluid from different compartments towards the blood to sweat. Is that right? If I'm following right?
Yes. And the point, yeah, okay. So I've got a bunch of I've basically just pulled up a ton of information on my other screen so I can keep pointing myself in the correct direction so I don't go too far. But an interesting thing that we see about dehydration is that the greater the magnitude of dehydration, the different compartments that it pulls from. So if you lose about 2% of your body weight from fluid, usually about 10% of that ish is from the plasma. About 60% is from the interstitial fluid, or the fluid floating between the vessels and the cells. And then about 30% is from the cells themselves. But then as we get that greater level of dehydration, there's no longer as much fluid readily available. And what happens is, as you pull fluid out the interstitial space, that concentration then goes up. So now the cellular fluid starts moving into that space, which generally it's meant to be going the other way. So because you pulled a load of fluid out of this interstitial space, the concentration shoots up. So then fluid moves into that section. And ultimately at about 4% dehydration, you're looking at still about 10% from the plasma. But now it's about 38%-ish from the interstitial fluid, and now 52% from the intracellular fluid. So once we pass kind of 3% dehydration, that's when we're starting to see that point where the balances have shifted in such a way that the body starts to very aggressively pull it out of the cells themselves. And when we think about what's going on in the body most, the function is happening inside the cells. Like the interstitial fluid is, I wouldn't say non-functional, it serves a lot of functions, but it's not serving as many direct functions, for want of a better term, than the actual fluid in the cells is. Now, obviously the plasma is serving a lot of fluid functions because it's carrying around blood. But it's interesting that as that dehydration gets larger, once we hit about that 4-ish%, it seems those percentages seem to stay quite consistent from there on out. But you're obviously losing very large portions from the cells because of that basically shift in concentration.
So let's talk about why that's important. Let's just say, I don't know, I've come to Dr. Ollie B. I go, hey, doctor, I've got a fight coming up. I want to do this. And we've done this whole diet plan, and then I'm going to go start sweating. We come to the point where I've got to cut some weight, and I'm, I don't know, let's say 5% over. I've got to weigh in at 70 kilos and I'm 3.5 kilos over. And you go, okay, Geordie, hop in that sauna, pal, and let's start sweating this out. And I sweat out 5%. Like you said earlier, you're taking these out from what it seems like after that 4%, mostly inside the cells. It's shifting through all these spaces. It's going on my skin. I'm getting hot. I'm sweating. My body's trying to handle that. We get there. I make weight. I go, thank you, Dr. Ollie. We give you a high five. But like you said, then I've got to somehow get this back into my body.
Yeah, exactly. And that's the bit that gets difficult, because essentially what's happening is the body is kind of, because it's osmosis. Osmosis essentially wants the concentration everywhere of water to be the exact same. So what happens is, as you lose fluid from these various compartments, fluid then just starts dancing around, and eventually you end up kind of in an equilibrium. Then what happens is you go, okay, well, I don't intend to spend the rest of my life 5% dehydrated. So time to start taking some fluid in. And now you're only able to affect one compartment, which is, I guess, the digestive tract, but ultimately the blood. But even then, if the concentration of what you're ingesting isn't ideal, it actually isn't uptaken into the blood nearly as well as it could be. So I'm not able, I cause damage to these three compartments, the plasma, the interstitial, and the intracellular, but I can't replenish them all at the same time. I can only replenish one after the other. And, you know, even if someone, I had this conversation before and people have gone, well, what about IVs? First of all, I see no reason and no convincing evidence that an IV is a good move, an optimal move for rehydration, unless they are unable to ingest something through the mouth because they keep throwing up. Then obviously it makes sense then. But the thing is that the digestive tract has evolved for, you know, hundreds, thousands, millions of years to do one thing, which is to get things into your blood in the right quantity. But even then, the IV is just putting it into the blood anyway. So you're not skipping any compartments. You're just really skipping the intestines. But the point is anyway that sorry, just as someone walking past my office waving at me, I'm like, I'm in a meeting, bro. But the point is, then all I can start doing is replenishing one area. And ultimately there is a knock-on effect, and how quick it, because you can severely dehydrate yourself, and you could rehydrate in the stupidest possible way, and technically you would still eventually be rehydrated. It's more because your body's pretty good at doing it. It's more just a question of how fast you can balance them out. And we have seen evidence in our lab and in data we've published that does show that it seems like this balancing act is not done 24 hours later from less than 5% dehydration. This was like 4.2% or something. And we saw evidence that 24 hours later, it still wasn't fully balanced out, which is very interesting, which is quite contrary to, I think, what a lot of people initially in sports nutrition thought about hypohydration or dehydration as being, which they initially thought, it doesn't, once you got the fluid back in you, more or less problem solved, let's not stress about it. And I think combat sports, or weight cutting in particular, but even just general sport, have kind of blown this out of the water. Now, to be fair, other sports have been much better managed than combat sports. So for example, generally when it comes to exercise science, the sports that we take as gold standards are usually endurance sports. Like if you think about how they manage cyclists in the Tour de France, that is more or less, cycling is more or less the pinnacle of exercise science. But for a lot of reasons. One of them being it's a pretty controllable sport too. You know, you can put a power meter on a bike and you can know the weight and incline and all that stuff. And power output is more or less a 1-for-1 correlation to who's going to win, like power output relative to body mass. So in that sport, they're very particular about how they're maintaining their hydration during an event and recovering from it. Combat sports is just like, yeah, bro, it's all good. Just get some coconut water, you'll be sorted. Like, it's very interesting to see the contrast between the two sports. I think I can't think. Have I answered your question? Honestly, I keep going. I just keep going.
Because I got a good question here coming out after it, because if that's true, then right, like if say, like, it doesn't even have to be combat sports. Say you shove me in a sauna and I'm making weight and I lost 3.5 kilos, I'm 5% dehydrated. I could be out running in the mountains or something and just not have access to water. I could be 5% dehydrated. The principle is still the same, right? That you would lose the fluid from that intracellular space.
That, I think, is actually a really important point to make, is that typically we think about dehydration in terms of intentional dehydration, but indirect dehydration, it's more or less the same. If when I live in Perth, Western Australia, which is basically like a giant oven. Our summer is like multiple days over 40 degrees Celsius, like over and over again. And I do a lot of running and a lot of various trainings, but like when I go for a run, especially in summer, I go early in the morning, but it's Perth, so it's never cool. And I sweat probably as much as a medium weight cut when I finish the run. And even then, exact same thing. So, or very similar thing, that fluid is still lost from the compartments in the same way that I talked about before. It's still as difficult to replenish as I talked about before. So it has a lot of wide applications beyond just weight cutting. Like a lot of fighters who are doing hard sessions are significantly or having a significant amount of dehydration from those sessions. It's not unrealistic to do a hard training session and lose 3% of your body weight in sweat. It's not unrealistic at all.
Yeah, absolutely. And I've recently gotten into ultra endurance.
Yeah, I've seen. You're crazy.
And the thing is, though, I've had to self-experiment on this. Exactly what you're saying, Oliver. I've had runs when I think more when I just started out and I didn't appreciate it. Maybe I was just working on other things and I just totally bypassed. I've ended up being 6 to 8% body weight dehydrated in this. And it's insane amounts because you're just out there for hours and hours and hours on end. But something I want to bring this back to is what you said here. It's still not balanced after 24 hours. And I think that's an important point, that not just for weight cutting, but say for athletes running the mountains, someone running in Perth out by the beach, someone on their bike, or someone playing tennis with their mates. If you're going past that 4% dehydrated, it could even take longer than 24 hours to get that fluid back where you've lost it.
Potentially. So obviously the way we look at this, there isn't. So one of the things that makes this a really difficult topic to talk about is part of the thing of the study I published that you're pretty aware of, I would imagine, which is reviewing the current methods of hydration in athletes. And basically that study is more or less me just complaining about hydration research for like, how many pages is this thing?
It's a big one, actually. It's a good paper. Can we get the title of that? Because I love this paper. Yeah. I actually routinely read this paper in my spare time.
So it's open access, so everyone should be able to get it for free. There's no paywalls. It is called Reviewing the Current Methods of Assessing Hydration in Athletes. It is by myself, Dale Chapman, and Chris Abbas. All those two are the great researchers as well. Obviously, very senior researchers as well. So it's really there. It was a great paper to work on, and it's basically just 11 pages of me going, "All right, listen up, motherfuckers. You're about to learn some knowledge. It's all ruined." And one of the reasons for that is we don't actually have a measure really. Some people might argue, but I imagine they'd be wrong, that we really don't have a measure of cellular hydration directly. When we think about how we assess hydration, we typically, and I've done this before on the podcast, so I won't go into it in a ton of detail, but the short version is you can look at urine, which is obviously not even one of those 3 compartments I talk about. We can look at blood, which is one of those compartments that we talk about, but maybe not the most important one because we want to understand the cells. There's really no direct measure of cellular hydration. Now, there is some studies that have looked at, and they're super old studies, which was pulling muscle biopsies, dehydrating them, and seeing the weight of the biopsy dry versus wet, and then looking at that at different times. But obviously a muscle biopsy is super invasive. For anyone who's listening who doesn't know, short version is you basically stick a thick ass needle into someone's leg with like a little hook in it, and you rip out a bit of muscle tissue, and then you analyze that. And there's a lot of issues with it as a method, but it also feels like getting Charlie horse, like when someone punches you in the quad super hard. Like it's not a good feeling, and it's not something you can just be regularly doing. So obviously a lot of this is based on looking at inferences from other methods and various other things that we could be looking at. And we're basically making estimations that cellular fluid is not fully rehydrated. I really want there to be a good measure of cellular hydration, and it's an area in the future that I'm trying to think about. But truth is, I don't think it's particularly realistic, at least at this point. You can do things like bioimpedance and stuff like that, but obviously that's all estimations of total fluid and unverified methodologies. Because when they go, oh, we can use BIS and that can tell you your cellular fluid, I go, how did you validate it? Because there's no measures, there's no gold standard measure of cellular fluid. So how did you, what? So it's very difficult to really know exactly. But what we are seeing is differences in hydration status measures 24 hours later, inconsistent results. We're seeing markers of decreased performance. We're seeing markers of increased mental fatigue potentially. And this is something that's not actually, this is well known anecdotally as well. So we've got this data, and then we can combine this to what we see practically, and it all kind of lines up. That, and there's a quote, funnily enough, I actually randomly ended up on one of my prompts with the Lance Armstrong quote, which is I probably started the day at 72 or 73 kilos and finished the time trial at 66.5 kilos. I don't know how it happened. When you're that dehydrated, the power just goes off. I tried to put it meaning water, all back in. You can't recover from a deep effort like that in 24 hours. And an interesting thing that we look at that for the hydration, but it's not just the hydration, right? When you do a bunch of exercise, there is a ton of things happening inside your body. One of the main ones being all your glycogen's getting burnt away. But replenishing all that requires water. And the water isn't balanced out. So actually having that optimal flow of water and having that fluid in the right place, that is very plausibly impacting people's recovery from hard trainings as well, which is super interesting and something that's very poorly understood right now.
Something I want to ask you, Oliver, because I'm sure people listening are going to be like, yeah, but I'll just go home, I'll take a pee, I'll look in the bowl, and that'll tell me. That'll tell me if I'm hydrated or not. What would you say to that person?
So probably the thing I'm most well known for, and be good or bad, is basically just constantly trashing on urine testing for hydration. And look, I actually don't mind being known for that because it's a good position. But basically, urinary hydration, again, if we think about the balance between compartments, that is exactly how your body does urine, right? And your body has no way of knowing the total amount of fluid in the body. It's got no way of knowing that. But all it's doing is it's going at the kidneys. It's going, yeah, water's not, the blood's not super concentrated. All right, let's kick out some water so that it can be concentrated. Or it's going, oh, this blood's pretty concentrated. All right, let's keep water so that we can stop it from getting more concentrated. There's literally the way that your body's making urine. And the thing is, if you dehydrate yourself, a hard training session, and you scull a bunch of clear water, well, it could be clear and have electrolytes in it, plain water, you scull a bunch of that, you then make the blood less concentrated, even though it's not back in the cells yet. And the kidneys go, oh, blood's not concentrated at all. Cool, let's start kicking fluid out. And ergo, you now have quite clear urine, even though your cells are still very dehydrated. So the urine assessment was not made for acute changes in hydration status. Like a urinary assessment of hydration is perfectly useful in everyday chronic situations. If you've done no exercise and you go to the bathroom and your urine is dark yellow, yes, very good chance that you're dehydrated. And if you go to the bathroom and your urine is clear, very good chance you're properly hydrated. But as soon as we rip massive portions of fluid out of the body and start rapidly putting it back in, that's basically when the entire premise falls apart. And it's ultimately not what it was designed for. It's like getting a hammer and trying to screw in a screw with it. It's like the hammer's a perfectly good tool, but it's not made for screwing. So I think it's not how it works.
So how do athletes navigate it then, Oliver? We don't have to talk about combat sports and post weight cutting. Let's just say the everyday person, or even if it's a combat sport guy just going to training, whether it's a cyclist just doing training, whether it's someone going to foosball or whatever it is. What's their best way for going about preventing dehydration to the point where it's going to be detrimental?
So it's interesting because now we kind of get into a different area, which is kind of talking about now. We've talked about dehydration, but now we're actually talking about managing it. And this is an area where there's been a great deal of debate. So the older recommendations from the ACSM used to be to drink as much fluid as you lose. Now, that's not the current recommended guideline. And I think you could probably understand this extremely well. If you've gone on your ultra endurance run and you've lost, I don't know what 8% of your body weight would be. Let's call it 6 kilos or something.
Yeah, about that.
It's quick math. So let's call it 6 kilos. And basically, if you then, how realistic do you think it is that you could drink 6 liters of water across that run?
They're very, very, very difficult.
Yeah. But not you. Basically, your stomach would just be slushing around all the time. You'd probably want to throw up, and it wouldn't even be back in the cells anyway. You're also carrying around the extra weight, which makes the exercise harder. It obviously maintenance is not possible during longer hard exercise. What the current recommendations are is to drink as much as you comfortably can and avoid dehydration of greater than 2% of body mass. And generally, when it comes down to the old question where there's a lot of debate, does dehydration affect performance? The general, I'm very hesitant to talk about the general accepted term because I'm probably going to get like 6 physiologists messaging me like, you're an idiot, bro. It's not what I think. But the general, if you've got a bunch of physiologists in a room and you polled them all, you'd probably get the majority of them to agree that dehydration of 2% or under doesn't seem to affect performance in any significant way, and over 2% does seem to affect performance generally. So obviously that's counting on the environment. If you're exercising in the heat, that becomes the effect becomes greater earlier. But the point is, if you can try to stop it from getting more than 2%, then that's usually the optimal strategy. Now, another general recommendation that's given is if the total duration of the exercise is under 1 hour, then cold water is probably just your best bet during. If it goes beyond 1 hour, that's when you probably want to start looking at things like glucose electrolyte solutions, because then what you're doing is you're replenishing, 1, the glycogen that you'll be losing, and 2, you're putting in salts to help keep those compartments balanced. And that's pretty important, which, bear in mind, when I say 1 hour, the 1 hour rule is really applying to higher intensity exercise, or like moderate or above. It's not like, I've done 1 hour and 5 minutes of light gardening, better smash a whole 1 liter of Maximus. Like, it's 1 hour of doing something that you are significantly sweating as a result of, I think, is a pretty good way to define that.
Oliver, here's a theoretical for you, because I always get this question, right, about the 2% dehydration. I think it's important people understand when we say that. Is that a hard and fast number of 2%? Okay, if you go exactly 2%, you're going to be doing this, or what are your thoughts on it? Or, can some people go 3% and then maybe others, even if they go 1%, they'll start feeling crappy? What are your thoughts on it?
So the problem is with looking at the percentages, it's not really a hard fact. It's hard to be it's difficult to have hard rules in science, if we're being honest. And 2%, for example, is assuming you started in a hydrated position, which a lot of people are probably starting trainings slightly dehydrated anyway. So actually, it might be less than 2% in that case. This is from a position where you were definitely well hydrated before. And it's not like but this is 2%, and it goes, oh, performance is good, performance is good, performance is good, performance is good. Oh, suddenly it's shit. Oh, it's falling apart. I can't run. It's a gradual scale. 2% is a general rule. Obviously, there is biological variation in everyone. You're going to see some people who can get a bit further, some people who get a little less, but it is a general rule that the majority of people would be within 0.5% of, where we start to see more. And that's usually because that percent is that point where your body starts pulling from the cells more than other areas. It's about when we hit that 2%. But again, there is variation, and it depends on the starting hydration. So I think it's best as a guideline, not as a rule.
Excellent. And we'll wrap it up very soon. Oliver, last question that I want to ask you. What would be your top tips? What would be your top tips for athletes who are worried about it? They want to stay on top of their hydration. What's your top tips for them?
The biggest thing I can state is pre-hydration. A lot of people show up to training and go, oh man, I'm training so hard. I got to stay hydrated. This is so difficult, when they're showing up from a day of work where they've barely drank any water and they're already kind of dehydrated. The main thing is you should be showing up to your trainings really well hydrated. Like, I show up to pretty much every one of my trainings I need to pee pretty bad. And I get to my training, I usually pee just before I start, and then I start training. Because once I start exercising, the kidneys will adjust and stop moving fluid to the bladder anyway. And then that is going to be lost in sweat. So the main thing I concentrate on very heavily is making sure I'm well hydrated before I go. I drink quite a lot of water anyway, and it's not because maybe it's because I'm a hydration researcher, but it's mainly just because it also helps me from sitting in my desk too much. If I drink a lot of water, I have to get up and pee a bunch, and it just keeps me moving. But the main thing is prehydration, and that prehydration doesn't need to be anything complicated. Water will do the trick great. Your body is amazing at rehydrating just with water when that entire balance between the compartments isn't messed up. It's super easy, barely an inconvenience. Body can do it easy. The thing when you are training, the most important thing I think is easy. The rules I stated before, which is basically as much as you comfortably can. And it's a weird thing. So I've noticed I don't know, because I don't train in a lot of other sports. I do running, but that's obviously by myself. I do lifting, that's obviously by myself. But I do a lot of combat sports, and I've only ever trained in really consistently football or soccer to some. And I didn't notice it in that sport, but we'll see. But one of the things I've noticed in combat sport is people go, no water, no water, no water. You got to get tough. I'm like, excuse me. What the hell are you talking about? So the main thing is to make sure that you are taking significant, or you're taking breaks to just at least get down little bits of fluid as you're going through. You're better off consistently having little bits of fluid than necking a whole bunch of it after like an hour of having none and going, okay, that'll sort me out. It's little bits consistently, I think, is probably the most important bit. Then the post hydration. And the post hydration is relatively simple, I guess, but it's mainly around obviously not everybody's not just weighing themselves. So you can't go, oh, I lost this percentage of my body weight, I have to have this much water. Generally, drink as much as you're comfortable drinking is usually fine for most people. If you're doing something like a weight cut, obviously you know all that information if it's very severe. If you're going to have a lot of dehydration, it's good to measure pre and post, but for the most part, you can just as much as comfortable. If you've been doing it for more than an hour and you had a lot of sweat, it'd be a good idea to think about having something with electrolytes in it. Now, obviously things like Gatorade, Powerade, Triad, all that jazz, depending which one it is. Obviously, you've got to take consideration for the sugars being taken in. Is that something you can have at this point in your training? Or does it fit in your total kilojoules? Is it practical? If so, happy days, great, because it helps replenish glycogen. If not, you might be looking at sugar-free options or something like that. But if you've sweat a lot, it certainly wouldn't hurt to take an approach that way. I think that pretty much covers what we know in terms of practically speaking. I think the one that in this, what I just talked about then, that has probably been most neglected would probably be the prehydration.
Yeah, I couldn't agree more. I think the one thing that I have learned from just doing this ultra endurance training is the importance of that prehydration. Like I said, like I could lose that much weight, which we said before is about 6 kilos. And I say that to people, and people are like, holy smokes. I go, but you got to remember, like, that's not me coming in dehydrated and dry. Yeah. Like I'm actively loading my body up. So I'm probably 2% higher than what I would have been anyway. So it's like, it's really like the total loss is a lot less than that. And it's something that when you experience that hydration while you're trying to work, and I think there's a lot of components we talk about, like the neurophysiology of your muscle, and then the neurophysiology of what happens mentally when that goes on. It's not fun either way you look at it when you're really dehydrated.
Yeah. And I think one thing we have to remember as well is we think about a lot of things that the human species is unique for in the animal kingdom. And one of the things we are best at, and we might be the best on the planet at it, is thermoregulation. And all you have to do is look at persistence hunting, which is basically in the savannah going up to a wildebeest, yeeting a stick at it and going, and then as it runs away, you just lightly jog after it for like 10 hours until it's so dehydrated and overheated that it just kind of gives up, and then you walk up to it and shiv it. Like, the point is, that's what humans did for such a long period of time. We're good at sweating. Sweating is not something that's bad, and dehydration is not something that's bad. It's excessive dehydration is not ideal, and it's making sure that we understand that we do our best to avoid dehydration, but it's going to happen. If you exercise, it's definitely going to happen. Like, if you do any kind of hard cardio over longer periods of time, there's a good chance that you're almost guaranteed to get some degree of dehydration. The thing is, if we can keep it to 2%, that is way better than being 5. If the lowest you can get it is 4, that is better than being 6. And it's basically just about trying to do it better, because your body is well adapted. As much as I've sound like I've trashed on the body's ability to manage its fluids today, it's actually really good at it. We just ask a lot of it.
Yeah, I think it's so important, right? Like with everything in sports nutrition, individualize the approach. Like, understand how your body responds to certain levels of dehydration. See how you feel with different pre-hydrating techniques when you're drinking during your training, or like Oliver, play around with certain things afterwards and see what makes you feel good. Because, like Oliver said, we're a survival machine. We're designed to be in that state.
Yeah, exactly, 100%.
All right, Oliver, I think let's wrap that up there, because I think that's an absolute cracker. And I think, if anything, I want to highlight with that episode just how complex hydration is. You've just heard it from the horse's mouth, who is one of the leading experts in the world in the area of hydration. And you can see how nuanced and complex it is. And everything that you say, there's almost followed by but if this happens, or if this happens. And there's so many nuances to this area. I hope that makes it very clear. Anything, any final remarks in that?
No, I think that's a really good point to make. And I think everyone should also note that obviously everything I have said is with the asterisks of, to the best of my understanding, based on the current availability of scientific literature, because this is an emerging field of research. There's still good work being done in this area, and it's complicated. So yeah, look, I hope everyone has enjoyed listening to this. I hope I've done a decent enough job at explaining some of the principles. Usually I get, I've got students for kind of 3 units across an undergraduate degree to kind of get this across. So very much crash course. But yeah, if anyone wants to get in touch with me or wants to ask anything, Twitter is probably the best place to do it. I kind of keep stuff there. I literally don't even know what my Twitter handle is. I think it is just at Oliver Barley. Yeah, at Oliver Barley. There, your Barley spelled Barley. Yeah, I didn't do anything creative with it. So yeah, just follow me on Twitter and tweet at me, and I'll message back.
All right, I think that's a good spot to leave it there. So, Dr. Oliver Barley, thanks so much for coming on again.
Thanks for having me. Appreciate it.